Hey everyone, today we're going to do binary long division using only addition, subtraction, left shift, right shift, and the equals operators. So here's an example of some binary that we can divide. So here's an example of what binary division might look like. There's a few different ways to do long division. You could just keep adding the divisor and seeing how many fit into the dividend. But in the worst case scenario, if our dividend is 3 billion and our divisor is 1, then we would end up with O of 3 billion time complexity, which essentially boils down to O of 1 constant time. In some cases, O of 1 might be considered more efficient, but in this worst case scenario, it is extremely inefficient, and we always want to assume worst case scenario. So let's look at all of our options. How do we do long division? Let's look at this example. So this is an example of 100 divided by 10, except converted to binary. Binary long division is a lot like regular long division, except we only use zeros and ones. So let's try to divide this. Like usual long division, we go down the dividend. Can the divisor 10, 10 fit into 1? No, it can't. Can it fit into 11? No, it can't. Can it fit into 110? No, it can't. Can it fit into 1,100? Yes, it can. So we would put a 1 here. And we would multiply 10, 10 by 1. And we would get 10. And we would subtract. So we would get 1, 0, or we would get 0, 1, 0, okay, first we would get 1 here, then we would get 0 here, and we would get 1 here. We would have to take the 1 from here and then turn this to a 2. 2 minus 1 is 1, so then we get a 1, 0, 1. So that should be right. Then we would bring down the 0th place here, and then do the whole process all over again. So when we think about this, it looks like we can use left and right shifting in order to bring down the zeros. If you're not familiar with bit shifting, all numbers are converted to binary. Left shift inserts a bit on the right-hand side, effectively multiplying the number by 2. And right shift takes a 0 from the end, which effectively divides the number by 2. But in this case, we're not going to be thinking of shifts in terms of multiplying or dividing by 2. We're just going to think about it in terms of tacking on zeros. So this is more efficient than adding because with every bit, we are basically doubling the divisor with each round. So if we had a divisor of 1, then if we left shifted, we'd get a divisor of 2, then 4, then 8, then 16, and so on. And because we're using bits, the time complexity of this would be O of n, or linear, with n being the number of bits that the dividend has. So instead of, if we were adding, that would be O of 2 to the n, where n could be 1 million for adding the the divisor over and over again. So instead of getting O of 2 to the n, we get O of n, which is a lot more reasonable. So if f of 1 is the time that the shifting algorithm takes, and f of 2 is the time that the adding algorithm takes. Then f of 1 would be equal to the log of f of 2 okay. So let's start off with writing our functions. Our function. Let's set our quotient or our solution to 0 first. Okay, then let's have a variable for how many times we're going to left shift our divisor until it's larger than our dividend. Let's just call it k. Okay, so for our first while loop, for as long as the divisor fits into our dividend, we want to keep left shifting until we want to keep left shifting our divisor and adding a 0 to the end of it until it's larger than our dividend, and we want to be increasing k. So while divisor is less than or equal to our dividend, then divisor is going to be equal to, we are going to left shift it, which is going to add a 0 onto the end, and we're going to increase k plus plus. Okay, then we'll start our next while loop. We basically want to go from k to 0. So basically, right now, if we were to let's just use an easy example first. For example, if we were to do 100 divided by 10, we would keep left shifting 10 until it is larger than the dividend. So let's take a look at what that would look like. Console.log divisor and dividend and k. And let's actually move that after here. Oops, sorry. Alright, we want to do divisor, dividend, and divisor in the function. Okay, so there would be 4 rounds. Basically, we would go from 10 to 20 to 40 to 80 to 160 until it's greater than 100. 100 in this case would actually just be 10, 10. That would be that in binary. So in this case, we would be tacking on a 0. So basically, what that would look like is we would keep tacking on 0. So we go to 10, 10, and then add a 0, then add a 0, then add a 0, then add a 0. So that would be k equals 4, and that would be 160. And so in order to be less than that, we would need to go back 1 to k is equal to 3. Okay. So for our next while loop, we basically need to go from k to k minus 1, and then we want to go from k minus 1 to 0. So I'm going to start with k minus minus. I go until it's greater than 0. inside the loop, we want to keep shifting the divisor right to counteract the way that we were shifting it left in this first while loop. So we're going to write divisor is shifting right by 1. So divisor is now equal to the divisor shifted right by 1. So every time we run this while loop, it's going to shift right to counteract us shifting it left. And then we're going to shift our quotient left. So that's to log all of our all the shifting that we did with our divisor. So basically in long division, what that would look like is, so at the end of the k, we would have 4, k equals to 4. Here we would have k is equal to 3. We would get this. And basically, this is to represent the 3 zeros that we would shift. So the first while loop, we would actually start with 4. It would be here. And we would want to shift the divisor right by 1. And we would want to shift the quotient left by 1. So we would add a 0 bit there. And then if the divisor is less than the dividend, then we want to subtract. So let's write a conditional if statement. If the divisor is less than or equal to the dividend, then we want the dividend to subtract the divisor, and we want to add the quotient, this one. So basically, if this is less than or equal to the divisor, which it is, we would want to subtract it, and now our carry down looks more like this. So let's subtract it. We would get this, and then we would add a 1 here to the quotient, and then we would repeat the process. So then we would have k is equal to 2. We would want to we would want to left shift the divisor like we just did. Then we would want to left shift the quotient. Okay, so does this fit into the new dividend below? Yes, it does. So we now have 10100. Uh-oh. All right. And does that subtract? That subtracts to 0. That subtracts to 0. And as a result, we're going to add 1 to the quotient again, because it's the divisor is less than or equal to the dividend. Then we're going to multiply 1 by 1010. Oops. And that's going to give us 1010 as a remainder. And then we want to left shift our quotient again. And then we want to right shift our divisor. So basically, our answer would be 10, 10, and this would be the remainder. Okay, so at the end of this, we would just want to return our quotient. Return quotient. All right, let's see if that works. Okay, that doesn't look quite correct. Are we missing anything? Oh, I put this in the wrong while loop. Okay. I'm going to move it down so it's you return it at the end of the function. Okay, so that's the correct answer for this one. We get 10. Now I'm going to try it for this one. We should get an answer of 1010, or rather that would be the binary answer. Okay, so as you can see, it's processing each of these steps, and we get a final integer answer of 1089. So let's just double check what this is actually an integer form. So we're gonna have 1100 divided by 1010, and that is correct. That is 1089. So that works. It works for both binary and for integer long division. So again, to summarize, the time complexity of this function is O(n), where n is the number of bits that the dividend has. And something that we should try to remember is that when we think of this in the lens of binary shifting, we're thinking in terms of long division, not multiplying by 2.